So to assign a systematic IUPAC name for each of these, we want to find the alkene, and the alkene should be located between 1 and 2 in a ring system. So this will be 1, 2, 3. And we also have to deal with stereochemistry at center 3 here. This is 1, 2, 3. I'll circle those. That's going in clockwise order. The hydrogen, or 4, is back. So that one stands as is. So that one is R. So this would be 3R, 3-bromo, cyclohexene. And this one here, we want the alkene to have the lowest numbering. If I number in the opposite direction, I get 8 either way, and the alkene is at 4 in both directions. The next thing we want to look for is if the lowest overall numbering. So in the blue direction, I would have 2, 2, 7 trimethyl. But if I numbered it in the red direction, it would be 277, which is higher. So I want to use the blue. And then we have 2 bromo groups at 4 and 5, and that will become first alphabetically. So 4,5-dibromo, 2,2,7-trimethyl, and that was 4-octene. All right, how many different alkenes can we make with the following substrates if it's treated with a strong base? So we'll start with drawing the structures. So that's pentane, 2-chloro. To do, if we did an elimination with the base here, we could end up with the alkene there, or one with the alkene there. This is probably the major product. For 3-chloropentane, I have hydrogens here and here. So this one has here. And those are beta to the leaving group. This is symmetric, so we'll just get one product. Okay, and then for this one, 2-chloro, 2-methyl. I have a hydrogen here. And this one is chemically equivalent, and then we have this one. So I have that product. And this one, and that would be preferred. Here to predict the major product, I have sodium hydroxide acting as the base. Here's my leaving group. And sodium hydroxide is a small base, so I'm going to grab the less accessible proton that will give me the more stable product. So I'll grab that hydrogen, those electrons come in to kick off the Br, and I form a double bond right there. T-butoxide is a large base, and that has a minus charge. That's going to grab the most accessible proton, and we get the less substituted alkene. Alright, here identify the major products for the E2 reaction when it's treated with a strong base. And in these reactions, if there's stereochemistry involved, we want a proton that is anti-coplanar. And so this would have to be on the back side of the chlorine. In this case it is. So we can just grab that one. So our chlorine's going to get eliminated. Methyl group is still here. We lose stereochemistry because sp2 carbons are flat, and we get a double bond right there. In this problem, the hydrogen is on the same side as the chlorine, so we need to do a rotation. We want the hydrogen and the chlorine to be in the plane, so I'm going to do a rotation here. I'm just going to rotate that up one position. So that's just a rotation. So if I draw this flat here, my hydrogen got shifted up to here. And then when I did that, the methyl group here is going to become dashed. And the ethyl group will just come around to this side, and that becomes wedged now. So on the other carbon, I'm going to draw in my hydrogen here. I'll just put it here as wedged. And then I'm going to rotate everything around one position so that chlorine becomes in the plane. The phenyl group is going to take the spot of the hydrogen, so that becomes wedged. I'm just going to abbreviate phenyl with PH here. And then the hydrogen is going to be dashed. So when we do the elimination, this can get picked up, and the things that are on the same side, so the phenyl group and the ethyl group are both wedged, those will be on the same side of the double bond. And there's the double bond that forms, and then the dashes will go together, so I have the CH3 and the H. And that is how you would do a problem like that. For H, there's a chlorine that's forward. I have two hydrogens here. One is wedged, one is dashed. I can just take the dashed one. And get that product. And this would be preferred because it is trans, or E. All right, when methyl chloride is treated with a strong base, only one elimination product is observed. Yet when neomenthyl chloride is treated with a strong base, two elimination products are observed. Draw the products and explain. So methyl chloride, this one has one product. I have hydrogens here that are beta. That one's on the same side, so I can't eliminate there, but on this one, I have two possible, and it's going to eliminate this. So the one product has a double bond here, and in neomenthyl chloride, I have a hydrogen here. There's two here. This one would eliminate. They're on the opposite sides. We're going to lose our stereochemistry where the isopropyl is. This stays the same. And our double bond forms right there. And in the other product, we can eliminate these. This isopropyl stereochemistry stays the same. The methyl group stays the same, and my new double bond is right there. So those are the two products. All right, predict product for each of the following E2 reactions. I have a small base here. So it's going to go for the more substituted alkene. So that would form. This is a bulky base. This is going to go for the most accessible proton, which would be the one over here. And we'll take the one on the opposite side. Double bond right there. Here we're drawing a mechanism. So OH is a bad leaving group. We have an acid present. which can protonate that alcohol to make it into water to make a good leaving group. So that's going to grab a hydrogen. So this is a proton transfer. Water is a good leaving group, so that's going to leave. So we have loss of leaving group. Carbocation, that's secondary. If I take this whole group here and shift it over here, that would make me a tertiary carbocation, which is more stable. And now I have a hydrogen right here that can get picked up by the H. SO4 minus from earlier. That can grab this hydrogen. That does an elimination. And that is the mechanism. All right, in each of these cases, draw the structure of an alkyl halide that will undergo E2. So we just got to find out where the alkene is, which in this case is here. So you can imagine before that, there was a leaving group there. So that's how you would do that one. For this E2, there could be a double bond or a leaving group here, or one there. So you can draw both of those. Both of those would give you the same product. For this one here, you can have a double or a leaving group there. And that would get you to that product. For this E2, my leaving group would have to be on the end. And I'd have to use T-butoxide to get there. If I try to put a leaving group here, when it does the elimination, it's going to go for the the more substituted alkene to give you that product. So if you have it on the end, then it only has one place to go.